Hello students and welcome to the Computer Organization and Assembly Language Lab. Today I will be implementing SAP one simple as possible computer. It's a minimalistic computer architecture which only implements a very few simple instructions in this assembly language. My name is Dr. Farhan Khan and so let's start with our lecture. Here you can see a block diagram of SAP one. The SAP one architecture consists of some components. It includes a program counter, an inputs and memory address register, a 16 by 8 RAM, an instruction register, a controller sequencer, accumulator, adder subtractor, register B, an output register, and a binary display or a 7-segment display. All these components are connected to each other through a W bus. This W bus is usually 8-bit. And now let's see what each of these units how these units work one by one. Let's go through a brief detail of the SAP1 architecture. The SAP1 architecture is controlled through a program counter, which is 4-bit wide. The program counter actually counts through different instructions of the instruction set. So it can count from 0000 up to 1111. So it can point towards up to 15 different instructions. For SAP 1, we only need 5. Then we have an input and MAR, an input register and a memory address register. These both functionalities are done through a single register. It includes the address and data switch registers. It sends 4 address bits and 8 data bits to the RAM. The RAM is then a 16 by 8 memory. There are 16 memory locations and each memory location is 8-bit wide. The RAM is then followed by an instruction register which loads the content of the addressed memory location through the W bus. The upper nibble goes directly to the controller sequencer. The upper nibble or the first 4 bits, the leftmost 4 bits in the instruction, because they are the instructions, so they control everything, so they goes directly to controller sequencer. The lower nibble is read onto the W bus when needed. The controller sequencer is the most important part, in a sense, of any computer architecture. Before each computer run, the CLR bar signal is sent to the program counter, which resets the program counter to 0000 or its initial value. A CLR signal is sent to the instruction register, which wipes out the last instruction in the instruction register. The CLK at the clock signal is sent to all buffer registers, which synchronizes the operations of the computer. And a clock bar signal is sent to the program counter. The 12-bit output that comes out of the controller controls the rest of the computer. The 12 wires carrying the control word is called the control bus. So there are 12 wires which are basically part of the W bus, and they are called the control bus. And the output of the controller sequencer is put on these 12 wires. This is how the control word looks like. So there are each of these values are either low or high. So CP, EP, LM bar, etc. The word determines how the register will react to the next positive clock edge. For example, if EP is high and LM bar is low, that would mean the contents of the program counter are latched into the MAR on the next positive clock edge. Another example is when CE bar is low and LA bar is low, that would mean that the addressed RAM word will be transferred to the accumulator on the next clock edge. The next component is the accumulator. It's a buffer register. It's 8-bit wide, so it can hold at a time an 8-bit number. When the EA is high, the content appears on the W bus. Then we have adder subtractor, which performs 2 complement adder and subtraction. When SU is low, it performs addition, such that the contents of register B would be added to the contents of register A or the accumulator. When SU is high, it performs subtraction in terms of binary complement. So that is that the contents of register B would be first complemented and then added to the contents of register A. When EU is high, the contents appears on the W bus. Since our simplistic architecture SAP1 performs addition and subtraction, so apart from the accumulator we need another register so which can hold temporarily to the data that is needed to be added to the accumulator. For that we have a B register, another 8-bit wide buffer register, similar to register A in the architecture. It's used in the arithmetic operations. When LB bar is low and positive clock edge, the word on the W bus will be loaded. Then we have an output register, which is often called the output port. When EA is high, when EA of the accumulator is high and LO bar is low, and the next positive clock edge, the accumulator word would be loaded onto the output register. Then we have a binary display, which displays the contents of the output register using LEDs, a row of 8 LEDs, and each LED connects to one flip-flop. Apart from the binary display, we can also attach a several segment display so that the numbers can be and the output can be seen in hex format. Any computer architecture is divided, categorized into its building blocks that are control units, ALU, memory, and IO unit. For SAP1, the control unit consists of a program counter, a controller sequencer, and the instruction register. The ALU is basically the accumulator, the B register, and the adder subtractor. For the memory, we are using MAR or the memory address register. And for the IO, we can use input programming switches, an output port, and a binary display. Let's go briefly through the instruction set and how they work. So the first instruction in SAP1 is LDA, which is short for load the accumulator. It loads the accumulator with the data from the RAM. For example, if the instruction is LDA5H, then from the memory location 5 in the RAM, the contents would be loaded onto the accumulator. So let's assume we have 10101111 at the memory location 5 of the RAM. This number would be added to the accumulator. So now the register A contains this number which was at the memory location 5 of the RAM. Our next instruction is add, which is short for addition. For example, add 3H, which adds the content of memory location 3H to the accumulator content and save the results to the accumulator. For that to work, the contents of R3 is first loaded to the B register, and then using adder subtractor, they are added to the contents of the accumulator. Then we have our third instruction in the instruction set, which is sub, which is short for subtraction. For example, sub 2H would subtract the contents of memory location 2 of the RAM from the contents of the accumulator register. It subtracts the content of from the accumulator content and save the results to the accumulator. And for that to work, the contents of memory location 2 is first loaded to register B. Then we have the output register. Then we have the out instruction, which transfers the accumulator content to the output port, and HLT halts, which tells the computer to stop processing the data. Note that the first three instructions, LDA, add, and subtraction, they are memory reference instructions. They need to reference the contents from the different memory locations, while the last two instructions, out and halt, are not memory reference registers. So it doesn't matter what these instructions are followed by. These short versions or abbreviation of the instructions are called mnemonics. The instruction set of SAP1 is upward compatible with 8080 and 8085 instruction set, which means that all of these 5 instructions could be used without any changes as the instructions or the assembly language for the 8080 and 8085. But there are many more instructions in the instruction set of 8080 and 8085 than just these 5 instructions. In SAP1, each instruction takes at least 6 clock cycles. So with one clock tick, part of the instruction is performed. These 6 clock cycles are divided into 6 T states. They are called T states, ranging from T1 to T6. T1 is called the address state, where the address from program counter is transferred to the memory address register. The control word during T1 is shown here. Then it's followed by T2, which is called the increment state. At the increment state, the program counter is incremented by 1, and the control word is given as 101111000011. Then we have T3, which is called the memory state, where the address RAM instruction is transferred from the memory to the instruction register and the control using the control word. Now these first 3 T states are common to all 5 instructions. The remaining T states differs from each instruction. For instance, if we are performing LDA routine, for example, LDA 9H, the instruction register contains 0000, which is for LDA, 1001, which is for the memory location 9. Then at T4 state, the 4 zeros goes to the controller sequencer because it's an instruction, and the 1001 goes to the memory address register. Then at T5, the address data word will be loaded to the accumulator. Now, as you can see that all the operations of LDA routines are finished complete with T5. So at T6, there won't be any operation, but that would be different for other instructions. The good thing about SAP1 is it's very easy to simulate, it's very easy to implement it hardware with very simple gates and buffer register and buses. You can implement it on your own. So here we would follow with a simple simulation of SAP1 in a circuit simulator. There are different options for circuit simulations. For example, Proteus, Model Sim, Circuit Maker, FSpice, etc. We would be using a logic circuit simulator called Logisim, which is very easy to understand, very easy to use. This, as you can see here, a schematic where we have implemented all the different components of the SAP1, and we can also implement SAP1 in Verilog and then load it onto FPGA, so to use it as a hardware implementation. Or you can make the circuit in Proteus and copy the circuit directly to a printed circuit board or PCB. So let's see how this simulation works. We will be using a circuit simulator called Logisim that simulates logic circuits with the help of logic gates and other devices. You can draw your circuit here by using these options. You can, for example, you can use different wires, GATs, plexers, arithmetic units, memory units, and so on, input, output. We've already built a circuit, so let's load that circuit, and then we can use that to simulate SAP1 architecture using this circuit. So this is our circuit. We have a counter, we have a memory address register, we have a RAM, which is basically a programmable ROM. We have an instruction register, a controller sequencer, a register A, an adder subtractor, a register B, an output, which is a binary display or a 7-segment display, and you can use this clock as input. You can, by clicking it, it would give it one tick of the clock. So by clicking it twice, it would give it one positive edge. And this clear button is used to clear everything. In the beginning, we don't have any data in the RAM, so you can load the instructions and the data bits to this RAM by using the edit contents. For example, you can edit values here and then save these values by clicking save, or you can use load image to load the already built program. So for example, I have loaded here some data to this RAM. You can see the first bit are 081928E0 and so on. The program counter would be used to point to the memory locations of the RAM. It would start from 000 and goes to 1111. So the first instruction that would be fetched would be from the first location of this RAM. So as you can see, it's 08. That means 0 is the instruction, that is load, and 8 is the location of what to load. So from the 8 locations of this RAM, which is 05, this number 05 would be loaded to the accumulator here. Uh, as you know that, as we studied that SAP1 used 60 states to load one instruction. So for to load to go through these 60 states, we would be actually clicking this button 12 times. So let's start the simulations. So let me click this first. 1, 2, 3, 4, 5, 6. So now you can see it points now to the 8th memory location, and the memory address register is loaded with the number 8. Then the instruction register is loaded with 08. That means load the contents of location 8 to the accumulator. The contents of location 8, which is 05, is loaded to the accumulator. The counter is incremented by 1. That means the next instruction would be at location 1 of the RAM. As you can see now, it's at 19, which means the second instruction, which is add A plus B. So essentially it would be first loading some contents to register B and then adding those contents of register B to the contents of register A. The contents that would be loaded to register B are at location 9, which is A1. So A1 would be loaded onto register B first, and then A1 would be added to 05 here. Let's see. A1 is loaded into register B, and now at accumulator we have the contents of A plus the contents of B, which is A6. The counter is incremented by a number, so now the counter is at 2. That means the next instruction would be at location 2 of the RAM, which is 2A. Now, from the instruction set, we know that 2 means subtract A minus B, 0010, which is 2. And now the contents of memory location A from RAM, which is 06, would be loaded to register B first and then subtracted from the contents of register A. Now at register A we have A0 because 06 is subtracted from A6. Now the next instruction, program counter is incremented by 1. So the next instruction is at location 3 or the 4th location, E0. E is for output, and the lower nibble 0000, it is a no care condition. So even if there is any other number, it would still not matter. So we are only interested in E. E, as we know from the presentation before, the last two instruction output and HAL are not memory connected. So now the output bus or the output register is loaded with the contents of register A. Now we have A0 at the output. We can also see this at the binary display. We have 10100000, which is equivalent to A0. And we can also see this output at the 7-segment display. The counter is incremented by 1. So now we have 4 at the program counter, and the next instruction that would be fetched from the RAM would be at location 4, which is F0. 0 here is a no care condition, so any other number would still work. The first number is important, which is F, and F is the instruction for halt, all ones. So it would halt all operations of the computer. Now you can see the computer is halted, so even if you keep on clicking this input button, it won't do anything. If you want to start all over again, you can click this clear and start all over again. The program counter is set at 0 again. So this is a very simple simulation. You can create this kind of circuit also in other circuit makers. There is simulation tools like FSpice, Circuit Maker, Proteus, or you can code the working of SAP1 in Verilog so that you can embed the code onto an FPGA, or you can use a model sim to simulate the working of SAP. So that's all for now. Thank you. Okay, so now let's implement our SAP1 in Proteus. Proteus is a very interesting circuit simulator. We can also build a schematic for which can be transferred then to PCB using this Proteus. The good thing about Proteus is we can use all discrete circuit components, especially for the logic gates, memory units, buffer registers, wires to be used as buses, and so on. So here you can see the OR of the program counter, the instruction register, the memory address register, and everything. Here we have some displays. This one displays the output of the value at the program counter. The T states, the control matrix, and the output, the contents of the output register. We can either run the simulation as a whole, but it would be very fast and probably it won't be easy to understand. Let's see. You can see the program counter values are incrementing, the T states values are changing, and you can see the final output at the output display. Or you can see what happens at each clock tick at 1 by 1. So by clicking here, so this at first T states the program counter has a value of 0. At the second T states, program counter value is incremented. You can also see the changes in the control matrix. We only have the display connected to the output register, so you would see only the word at the output, which is from the accumulator, once the out instruction is executed. So let's see. Okay, let's keep on clicking. We have now at the third instruction, at fourth instruction, which is out. So the contents of the output register are displayed here, which were actually from the accumulator. And our memory is here. This is let's look at different components. This is our program counter, this is our instruction memory address register, this is our RAM. If we click on it, here we have loaded an image, a hex file, which contains different contents of the RAM that's loaded onto the RAM. Basically a series of instructions, and followed by the binary data that is loaded onto the RAM. Then we have a controller sequencer. We have a W bus here. We have an accumulator here, an adder subtractor here, the B register, and the output register. Let me pan it a bit. So this here is our output register. All the components of the schematic are built from the discrete circuit components, logic components, gates, we have gates, we have registers, we have buffer register as well as memory registers, and so on. So you can also try this schematic which I'm going to share on your own. You can change the contents of the RAM, you can change the sequence of the instructions, and then see what happens. Okay, that would be all. Thank you.